Hey everyone, and welcome to this explainer. I am absolutely thrilled to have you here today, because we're going to tackle one of the most fundamental, yet honestly, universally misunderstood topics in the entire GCSE Physics curriculum. We are talking about energy. Today, we're going to completely dismantle everything you thought you knew about how energy actually works, and we're going to rebuild it using the exact framework examiners want to see. Get ready, because this is going to completely change how you view the physical world around you. Before we really get into the nuts and bolts, let's start with a bit of a universal paradox. We hear it on the news literally all the time, right? We are running out of energy. We need to save energy. But wait a second. If there is one absolute, unbreakable law of physics that we're taught from day one, it's that energy is perfectly conserved. It never disappears. So if every single joule of energy is still here, how can we possibly be running out of it? Just hold that cognitive dissonance in your mind for a bit, because resolving this paradox is exactly what we're going to achieve by the end of our time together today.
Okay, let's dive into this. Here's our roadmap. First, the great energy misconception. Second, the conservation of energy. Third, 8 stores, 4 pathways. Fourth, the particle model. Fifth, specific heat capacity. And finally, where does energy go?
Section 1. The great energy misconception.
You know, the biggest hurdle in physics isn't actually the math, it's our everyday language. We use words in normal life that mean something totally different in science. Research actually shows that a massive percentage of students treat energy like a physical substance, kind of like a glowing, magical liquid that flows through wires, gets consumed by a light bulb, or is used up like fuel burning away. Listen, treating energy like a consumable fuel is a massive mistake, and it will definitely cost you marks. Energy is not a thing you can hold in your hand. It's essentially an abstract accounting system for the universe. We need a completely different model.
Section 2. The conservation of energy.
Energy cannot be created or destroyed, only transferred. This is the law of conservation of energy. It is absolutely crucial. Every single joule of energy that existed at the Big Bang is still here in the universe today. Not a single drop has been lost, not a single drop has been added. The universe is a perfectly closed system, and the accounting books must always perfectly balance.
And this brings up a really crucial shift for anyone sitting exams right now. For the 2025 to 2027 examination series, you're actually provided with formula sheets. This is a game changer. Examiners no longer care if you can rote memorize a string of letters. They are testing your deep conceptual understanding. They want to see if you can apply these principles, like conservation, and mathematically rearrange those equations to solve real-world problems. Your value is in manipulation, not memorization.
Section 3. 8 stores, 4 pathways.
So, if energy isn't a substance and it's perfectly conserved, how do we track it? Well, we shift to the modern framework used across all major GCSE boards, stores and pathways. Imagine energy as money, and these 8 stores as the different bank accounts where the universe keeps its cash. We have the kinetic store for moving objects, gravitational potential for objects lifted high up, elastic potential for stretched or squashed objects, thermal for hot objects, chemical, which is the energy in food, batteries and fuels, nuclear locked inside atoms, magnetic between interacting magnets, and electrostatic between interacting electrical charges. File these 8 macroscopic stores away in your mind. Whenever energy is just sitting there, it's in one of these accounts.
Now, what's really interesting is how the money actually moves between these bank accounts. It doesn't just teleport. It has to take one of 4 active pathways. First, mechanical work. That's a force moving an object. Second, electrical work. Charges moving through a circuit. Third, heating. Energy moving from a hotter object to a colder one due to a temperature difference. And fourth, radiation. Energy transferred as a wave, like light or sound. So the key takeaway here is, stores are where energy is kept. Pathways are how it actively moves.
Section 4. The particle model. We've looked at macroscopic systems, right? Big objects, like springs and cars. Now, we need to zoom in to the microscopic world inside matter itself. When we look at a block of ice or a cup of water, we are looking at billions of particles. The concept we use here is internal energy. By definition, internal energy is the total kinetic and potential energy of all those individual particles combined. Notice that it has 2 distinct components. We have to track the kinetic energy of the particles and the potential energy of the particles.
And here is where so many people drop marks, so pay close attention. We absolutely must draw a hard line between these two. The kinetic energy of the particles is entirely related to their motion, how fast they are vibrating or zipping around. This is what we measure as temperature. The potential energy, however, is related to the spacing between the particles, the bonds holding them together in a specific state of matter. Temperature and state changes are driven by different energy stores at the microscopic level.
Let's walk through the timeline of heating ice to really lock this in. Initially, the solid heats up. The energy supplied makes the particles vibrate faster, so kinetic energy increases, and the thermometer shows the temperature rising. But then it hits 0 degrees Celsius. The ice starts to melt. During this change of state, the temperature stays completely flat. Why? Because the energy being supplied is no longer making particles move faster. It is actively working to break the bonds between them, increasing their spacing. The energy is going into the potential energy store, not the kinetic store. Once it's fully melted into a liquid, the temperature can start rising again as the kinetic energy increases once more. Never confuse heat with temperature.
Section 5. Specific heat capacity. Let's apply this microscopic understanding directly to one of the most high-yield required practicals in the curriculum. This experiment asks, how much energy does it take to raise the temperature of a 1 kilogram block of a substance by 1 degree Celsius? The setup involves a circuit with a heater inside a block of material and a thermometer. But here is the secret to the whole practical, the part examiners love to test your working scientifically skills on: insulation. If you don't wrap that block in thick insulation, the thermal energy you're trying to measure will just transfer right out into the surrounding air. You have to trap the energy to accurately measure the change in the thermal store. And here is the math that goes with it. The change in thermal energy equals mass times specific heat capacity times the temperature change. Remember, you'll have this formula on your sheet. The real test is whether you can manipulate it. If an examiner asks you to find the specific heat capacity, C, you just need to use the algebraic balance method. You isolate C by dividing both sides by the mass and the temperature change. The math physically represents how energy, mass, and temperature are intimately locked together.
Section 6. Where does energy go? Let's bring our narrative full circle and finally resolve the paradox we introduced at the very beginning. If energy is perfectly conserved, why do we say it is used up? Well, the scientific truth is a concept called dissipation. When we use energy to power a light bulb or drive a car, that energy doesn't disappear. Instead, it spreads out. It dissipates into less useful stores, almost always ending up as thermal energy in the surrounding environment. The wires get a little warm, the engine gets hot, friction generates heat. The energy is still there, for sure, but it's now so wildly spread out into the universe that it's entirely unavailable for us to do further useful work with it. We haven't destroyed the energy at all. We've just lost our ability to harness it.
So the next time someone tells you we are running out of energy, you can politely correct them. The universe's bank account remains perfectly balanced, right down to the absolute last drop. The energy hasn't gone anywhere, it's just dissipated into the background warmth of the cosmos. Which leaves us with a final thought. If every single joule of energy since the Big Bang is still perfectly accounted for in this grand, unbreakable system, how will you choose to transfer yours today? Keep questioning, keep learning, and I'll catch you in the next explainer.